Hello, everybody. I'm assuming you all can see us. There's a lot of juggling between different technologies happening. So I'm going to start with just a couple of slides to get the panel going. A second. So there are a whole bunch of sponsors. And Edge Impulse is one of the platinum sponsors. So is Habana, Efinix, Lattice, Mindbody, and Think Silicon. Those are the other sponsors. So just general, housekeeping suggestions here. If you're using the Hua app to listen to this presentation, there is a tab there for question and answers. Feel free to post your questions. I'll pick them up and post it to the panel if it makes sense. Feel free to stick around even after the panel is done. You can post the questions anytime theoretically, and one of the panelists, if we have the time, we'll definitely try to answer them. Feel free to connect with us if you need to engage more deeply. That's also a polls tab, pretty interesting, real time. See if we can make use of that. So here are the panelists and the panel moderator, myself. So Zach, he's a co-founder and CEO of Edge Impulse. Stephen Bailey, a co-founder and CTO of Syntiant, and Janakiram, who's a principal analyst at Janakiram Associates, and myself, Arun Rajasekaran. So that's going to be a short and sweet, just highlighting the name and the title of all the panel members. So I would actually like the panel members to take a minute or so, giving a brief intro and giving a few words of wisdom before we jump into the questions. So let's go clockwise. Zach, do you want to start?
Thanks, Arun. Hi, everybody. Just a bit of background on myself and why I'm really interested in what we're talking about in today's panel. I spent about 20 years in the embedded industry, co-founded one of the first IoT companies. And what I found is that when we're doing just IoT, we're really wasting a lot of the compute power we have on embedded devices. So to solve that problem, I co-founded Edge Impulse to help really make use of all the compute we have available and embedded and do a lot more with data, solve data-driven problems for everyday engineers and developers. So really excited for today's panel.
Thanks, Zach. Stephen, please.
Yeah, thanks, Arun. So I have a background in lots of what would be considered more cloud and server-side technologies, I would say, compared to where we are with Syntiant. Like Zach, I felt that there's an opportunity to bring basically deep learning as a computational tool to the edge and drive a disruption in what we believe mostly interface. I think is where we see deep learning having the first big impact on the, at least when you get out to the clients. Obviously you can run servers at the edge too, or a car is an edge device, but it's running a rack of servers in the trunk. So that's what we started 4 years ago, and we're excited to see the road rise in front of us in terms of people's understanding of what you can do with the technology and how it can fundamentally change the way we interface to the digital world and it interfaces with us.
Awesome. Janakiram, please.
Hi, my name is Janakiram. I'm based out of Hyderabad, India. So my background is predominantly infrastructure and cloud services. Spent more than a decade at Microsoft, followed by AWS. And for the last 7-8 years, I've been working on connecting devices to the cloud. So I've seen the evolution of devices connected to the cloud, then ingesting data to the cloud, and now machine learning coming to the devices. So it's a very fascinating world of running deep learning models and neural networks right in the microcontroller and bringing the power of ML and AI to the last mile. So I currently work with platform companies as an advisor, particularly in the space of edge computing and transfer learning.
Awesome. So let me stop the slide share so that you can hopefully see the panel members with a little more pixels in your screen. So let's jump into some interesting questions. I mean, this field is so hot and amazing, in many ways. For folks to have been involved in it, whether it's Edge, Impulse, Syntiant, or even Janakiram, who has been giving lectures about this, to see this happening a few years back, right? That's needs a lot of vision. Because now there used to be this Internet of Things and edge compute, and now literally smarts coming in to the real endpoint. It's amazing. So the first generic question that I wanted to make post to the panel members is, from your own perspective, what do you think is the most underappreciated? There are a lot of benefits now. That there's even a poll I posted for anybody joining this session. The benefits of doing edge compute and adding smarts to the endpoint. What do you think is probably one of the most underappreciated? Let's go the reverse direction. Janakiram, you want to give your suggestions, opinion on that?
Right. So the most underappreciated factor is undermining the power of these devices. As Jack said right at the beginning, these devices are becoming increasingly more and more powerful, and there is a lot of heavy lifting that can be done right at the edge. So today, the definition of edge is changing from running highly constrained to more of powerful. There is heavy edge, there is a medium edge, there is micro edge. So the most underappreciated factor is undermining the power of what you can do right at the edge in a completely autonomous, completely disconnected mode without any reliance on data center or cloud.
Awesome. Stephen, what do you think?
Yeah, so I guess underappreciated, it's hard for me to put that into my own context, but what I can share is what I view as things that when I talk to people, I wish they already understood. And of course I could be wrong, but essentially I do think it's this divide between application and interface. So when we talk about deep learning, we talk about compute, we talk about smarts, all that kind of stuff. I think for our edge, which is basically terminals, that's kind of missing the point. You're viewing interface as a workload and viewing it as smart. Yeah, it resonates okay with people, but really it's all about natural. And deep learning is a computational programming model that allows you to interface with the natural world, which is super complicated. Okay, so when we built our first device, we had basically, it was limited to a maximum input vector size of 2K bytes, and so to illustrate the dichotomy, we said, okay, we can recognize words and sounds, or we can recognize tweets. 140 characters, is it the 45th US president or not? So the latter is more like an application scenario, and then obviously the former is interface. And I think for where we focus, interface, and talking about that as intelligent is less relevant than talking about it as natural. And so I really think that's how I think people should start to understand what's happening. So
that's a great point. Human machine interface, which I think Syntiant has been saying for quite some time, whether it's using as a voice, a touch, or gestures, or whatnot.
Sensors, input, output, all of it, making it more natural, both for humans and also the physical world itself. It's also very complicated independently of humans too. So I think that rises first and drives a lot of interesting application related things too, once you can build on that.
Great point. Zach, please.
I have a couple things that come to mind. The obvious ones that we talk about all the time are power, bandwidth, and cost, right? It's moving these workloads to the edge. But I think there's a more hidden layer that I think we should all spend more time on, and that is privacy, right? By bringing a lot of this computation and this, the complex patterns that we want to detect, whether it's for industry, right, or for humans to make a more natural interface. If we can detect those keywords, audio, people's faces, people's hand gestures, right on the edge, we bring a whole nother level of privacy. We only move the, the answer to the cloud. I think that's underrated, just how important that is and how big of a difference it makes. People don't understand that a lot of the human interaction systems we use today in mobile, for example, or in Amazon Echo, it's Amazon Echo, no, it's Amazon Alexa type devices, right? That all goes to the cloud and then it comes back to the device. But the future is going to be that we can do all that processing right on the edge. And in industry, we have a similar parallel, which is this is on device inference, right? This is on device processing. We get a lot of feedback from industry that, oh, I don't want my data in the cloud, right? I don't want to process anything in the cloud. What happens in my factory, right, should stay in my factory. And I think they don't quite understand yet that machine learning inference right at the edge means exactly that, right? It means that the data isn't going anywhere else, but they still get caught up in data sets. Well, we got to do some training in the cloud so that all my data is public. No, it's not. Of course, we're going to do some high intensity training early on in the cloud, but that's laboratory work. That's R&D work. Once we go into production in the factory, right, everything stays in the factory.
Yeah, no, fantastic point. So, the first question I posted for the poll for anybody joining this session, I listed the most trivial ones. I didn't mention interface, but I did list privacy, reduced latency, enhanced accuracy, reduced bandwidth need, effectively leading to less power consumption, reduced cost. And then I also gave all of the above. Interestingly, out of 28 respondents as of now, 75% said all of the above. So there are numerous advantages, some explicit, some implicit. But interestingly, the one that got 0 votes is enhanced accuracy. Maybe if we had a lot more time, we could talk about it, because one thing that is also underappreciated from my point of view is now you have high resolution data right there, right? Instead of you picking and choosing and doing some pre-processing and sending to the cloud and losing some subtle useful information, doing edge compute probably has an opportunity to uncover information that normally might not be possible. When you have
you're very far ahead of the curve on that, Arun.
Yeah.
I think most people haven't seen it from the vantage point you have, but
yes,
I agree. Yeah.
No, so maybe that's why it got 0 votes. But that's a great point. I want to keep an eye on the clock, because 30 minutes can go by so fast. So thanks for your responses. And I want to jump into something which I've heard Zach mention it several times. My involvement with Edge Impulse has been only for a few months, but there's so much I'm learning, kind of being part of their team. He mentioned this term Brownfield, and that's a very powerful thing. I think there's still some ways for even myself to understand this, but I would like in each one of your opinion. Janakiram mentioned some of this. I know Stephen approaches through Syntiant this phrase Brownfield in their own way. I would like each one of you to comment on what you really mean by Brownfield. I'm sure it's a very lengthy response. If you were to give a heads up to the audience, those who will also probably watch this recording later on, what exactly is this Brownfield opportunity from your point of view? Zach, why don't you start?
Yeah, so in the embedded device industry, it's really simple. Brownfield devices are devices that are already in field or already in manufacturing. So the SKU exists, right? We can't touch the hardware, but we can touch the software, right? Purely software update. And in the context of machine learning, that means we could add new machine learning algorithms, right, to one of those existing brownfield devices. And that's magic, right? We have hundreds of billions of these devices already out there. If we can add something to them to get people started, we can start to unlock the value. And then, there's a saying, if you start to eat, you get hungry. When you start to use a little bit of machine learning, you see all the things it can uncover, more advanced cases, audio, computer vision. People want to add more to their devices, but we don't want them waiting, years for a new hardware cycle in order to start putting new functionality in devices, especially during silicon shortage, right? Where we don't even know when we can upgrade a lot of these devices with new silicon.
Yeah, no, great. I mean, that's a very powerful statement, right? When you can add value to something that is already existing without having to, go through some costly respin. But, Syntiant perspective, you do need for a core processor to be added, but still there is some brownfield opportunity and applications that existed early on now probably can be solved in a lot more interesting ways, in efficient ways. So what do you think, Stephen?
Yeah, I agree. I mean, I think there's whenever you deliver a product to the market, the easiest thing to deliver is something that does something totally new that people know that they want. Okay, now those two rarely go together. But that's great. That's great when it happens. But the rest of it is about either delivering the same something differently, or trying to get people to learn new things to want. So delivering the same thing differently, I think, is how we look at Brownfield. And what that means is, for example, voice assistant on my Android phone or my Apple phone, which I have one of each. It's a fairly, the wake word subsystem is complicated, actually. It has a leaky first stage model that's always listening, and then it has a confirming model that runs in the AP to provide high performance. In Syntiant's case, we run the equivalent of that confirming model in less energy, in about 1/10 of the energy of the leaky model. Okay, so what that allows you to do is two things. One, it allows you to put voice assistants everywhere, because that engineering process for a given word is very complicated. So, Apple has it, and HeyG, and Amazon, there's a few, but other than that, it's hard to insert. So if you can do the whole thing self-contained, it helps. It also allows you to put it literally everywhere where you may not have that robust processor. So one form of Brownfield is things like that, where you basically say, all right, voice assistants are great, put them everywhere. And I mean everywhere. Okay, it doesn't matter battery life. You can have the thing listening for half a year, whatever. So that's one dimension. The other one is adding these types of more natural interface capabilities to systems that are already fairly well understood, right? And again, there's always like if you think of a medical piece of medical equipment, there's a lot of complexity of navigating through menus and pushing buttons, which requires specialists who know how to operate that equipment and that alone to support the doctors. Whoops, sorry, my Alexa is talking to me now. Hit the red button. Whereas if you can basically take that and make the interface natural, same kinds of outcomes a lot more efficiently delivered, right? So I think those are the areas where we find very fertile ground in terms of customers wanting to buy the technology. It doesn't create a lot of great headlines in the in the press, but that's actually where it makes a difference today, where people can understand what you're offering. So that's what I think.
Great transformation. Yeah, now in impacting what society needs. It's already doing today, but in a lot more efficient manner.
Exactly. Yes.
Yeah, awesome. Thanks, Stephen.
Microsoft Office.
Janaki, please, what do you think? You've seen, over the years, I remember 10, 15 years back, you were a visionary. At that time, IoT was not even there. And I remember, watching a lot of your webinars with awe. So there's a brownfield that's always going to exist, right? I mean, what the world is investing in. So how do these things, some of the things in the edge compute specifically that we're doing, is going to, from your point of view, revolutionize things that you are invested in already?
Right. So for me, brownfield is all about the traditional protocols that are infused and embedded into these devices, because machine learning is all about data. Even to train a model, even for inference, the way we acquire data from these existing brownfield devices is predominantly through traditional legacy protocols like CAN bus, Modbus, the RTU, and some of the very OPC UA and very traditional protocols. So unless we work with what is there in this industrial environment and use these existing protocols to acquire data and to send the commands back to control these actuators and devices, it's very hard to demonstrate and show the value of AI and ML at the edge. So for me, brownfield is all about protocols and making sure that we are interoperating with what's already there in the industrial environment.
Great. That's a technology brownfield you're saying, right? So that has to be backward compatible with a lot of things that we already do. I think each one has a unique perspective on it. So, this topic, brownfield, probably we can have a full day discussion seminar. One of the brownfield stuff that I learned working with Edge Impulse folks is adding, let's say you have a pressure monitor which has analog meters in it, and these are deployed as part of oil and gas exploration in Siberia, Alaska, whatnot, bringing in a computer vision device and making it sit in front of an analog meter, capturing that information and sending it back to the cloud. So it's devices that have no technology at all, but then supplementing with very low cost efficient devices. And to me, that was also a powerful brownfield opportunity. Might not be zillions, but these things add value to places where you cannot fly somebody to Alaska every single time, right? So the opportunities are endless. Zach mentioned something, and I'm sure all of the other panelists would also agree. What I want to get your opinion on is this powerful combination of silicon and software. Stephen is representing Syntiant, which is a new breed of neural compute. Zach has spent years at ARM, and I have been in the silicon space myself, and Janakiram, and I'm sure he has a good understanding of it. But both these, there's a potent combination that needs to happen. Cloud has a lot of degrees of freedom. There is not many constraints, but what we're talking about here is edge compute, micro edge. Janakiram has some input in this. So maybe a minute or so from each one's perspective. Is this an interesting intersection? If you look at it as a Venn diagram, are we in this cusp of right type of software in a brownfield as well as forward-looking silicon? It's just going to this potent mix that's going to really accelerate what's going to happen in the edge. Zach, you want to give your opinion on what is this magical? And you lead a software organization, but really it also still end of the day relies on what the silicon needs to do.
Well, I think there's a couple angles here. One is that we spent the last 5 years doing the fundamental research around TinyML. So taking the best of breed techniques from the cloud world and making these models smaller and smaller. And that's gotten us pretty far. I'd say we're at like generation 1 of embedded machine learning for small hardware compute. And so lots of amazing optimizations have gotten us to the point where we can deploy keyword spotting type algorithms down on even Cortex-M 0+ and very, very, very constrained applications, Cortex-M4s. We can do low-end computer vision on Cortex-M4s into M7s. So we've gotten really far with just pure software optimization of machine learning. But that's just the beginning. I do see that we've got a second and maybe even a third generation of software optimization techniques in the pipeline. New research that we've seen, like we just announced, that we'll be bringing object detection, a whole new architecture for object detection that is 10 times faster than what we've seen before in object detection. And that will bring us down from doing object detection on Cortex-A parts, right, down to Cortex-M, which we've never seen before. So lots of stuff happening in the software. But remember, right, embedded is extremely diverse when it comes to hardware, right? There is literally 100 to 200 to 300 different embedded hardware targets that we need to be able to run these machine learning algorithms on, because different industries have very different requirements. We have lots of wireless and wired communication protocols. There's security requirements, industrial, so many things that affect the embedded parts that we choose. Mm-hmm. And our job, as software tool vendors, is to make sure that all of our software optimizations work across a very diverse range of hardware. And then we have acceleration coming, and I'll let Steph talk about what's happening with Syntiant acceleration. I think is super fascinating, but we're kind of seeing that throughout the whole range of hardware. Already in high-end Cortex-M, we see things like the ARM Ethos U55. We just announced the first part that will be supported. That's a really interesting kind of new neural processing unit accelerator. And we're seeing already lots happening in the Cortex-A side, low power acceleration into GPUs.
Yeah, no, that's it's amazing. There is no silicon only solution, even though there might be some really hardwired solutions that some vendors might be posing. But optimization, so effectively, I can kind of predict what Stefan is going to talk about. Syntiant is really taking that, doing acceleration the silicon. Still, it's a order of magnitude different compared to doing software optimizations. But when both these things happen together, now the limits are just completely blown away. So effectively, the performance curve across the board with software optimization. Silicon acceleration is going to be doing some magic. So Stephen, why don't you touch on that,
Yeah,
that potent combination?
sure.
Please.
So I mean, I think deep learning as a programming model is all about overkill of computational density and degrees of freedom. That's how the programs get written. If you don't have it, you don't get a deep learning program and you don't get the magic. So in that sense, personally, I think that in a way, I mean, software is the most important thing. It's the most interesting thing. But you have to bring a high density of compute and state space to the problem, to do really interesting things. And the gap between the Syntiant core processors and the A's and the M's is usually about 100x in terms of efficiency. It's pretty consistent. We compare the 100 generation to the M4, which is common there, and we compare the 200 product to the A53, and that return is consistent. So it's not something you would spend days and weeks and months discussing, but that is how you bring really awesome deep learning to the program, right? And that's it's just an essential ingredient. It actually is not the star of the show. Deep learning is the star of the show. You just need to bring enough to allow the models to run.
Mm-hmm. Yeah. No. Thanks for that, Stephen. Janakiram, since you are more of a generalist, Stephen represents the silicon space. Yes, software, they do software part of it, and Zach represents the software space, but they do interface with silicon. Just to mix it up a little and keeping an eye on the time, maybe we'll start with you to wrap up the panel, as well as I know you have some put some thought into transfer learning. All we're talking about today is inferencing. That by itself is a big problem to address and solve. But maybe there are some hints of limited amount of training happening at the edge, and I know you have written and talked about it. So why don't you, talk about what is potentially ahead, maybe 3 to 5 years, and we can, have Stephen and Zach also conclude on what is ahead theme. Please go ahead. You're muted, Janakiram.
Yeah, absolutely. This is a good segue. And I also want to kind of continue the thread that we started off, the magic of hardware and software, the microcontroller and the edge. So when we look at what is going on in the enterprise data center and cloud, there is some kind of a convergence that is taking place. For example, there is Onyx, the open neural network exchange, which is becoming the lowest common denominator. Whether you train for a CPU or a GPU or an FPGA, Onyx is becoming like the new JVM, the Java virtual machine, where you could bring bytecode and abstract the underlying hardware. So Onyx is one such example. And then vendors like Google and Facebook are optimizing TensorFlow and PyTorch for GPUs and CPUs and so on. So we have TF Lite when it comes to TensorFlow. But while the first generation of running AI at the microcontroller level is very fascinating, I think the forward-looking view of that is all about optimizing further and creating a much more abstract common layer that will hide the complexity of the discrepancies we have across multiple microcontrollers and these devices, and bring some of the best practices that we have seen at the data center and cloud all the way to the edge. Things like Apache TVM and Onyx and some of the best practices that we have seen in the data center and cloud world will eventually come to the edge and microcontroller. And that is where we'll see all the interesting things happen.
Yeah, that's great. We have less than a minute left. I'll let Stephen and Zach give their wrap up. Thanks, Janakiram. Stephen, your parting thoughts?
No, I think you covered it. Thank you.
Thanks, Stephen. Zach, your view on what is ahead next 2 to 3 years?
So further optimization, cross-optimized for hardware. So like what we're doing to match the right software techniques to, for example, Syntiant's parts for very low power or for higher performance acceleration. But the thing we haven't talked about is that really what we have to get better at in the future is data. So machine learning models and techniques for optimization, great. That's plumbing that we need to provide. What really matters is the custom data that industry practitioners, right, the people in the factory or producing the model for hand gesture recognition or hard hat detection in construction, you name it. There's so many applications, but it's the people who have access to that data. That's where the real value is. And we have a lot of work to do to train everyone on how to take advantage of data, build very customized data sets, right? What's the best practice for getting the most out of those data sets and improving your model performance through data? That's the real hard problem. And we're only at the very beginnings of making that an easier, better, more powerful process. So I'd encourage everybody looking forward that don't get too caught in the weeds of the bits and pieces of tech. We're making that all happen, right? There's all the right things going on to make software and hardware optimizations awesome and getting better going forward. But everybody has to be really good at data, right? Every single person involved in this needs to know how to leverage data, just like we leverage code today. Think of it that way.
Complexity kills, it's a popular phrase. I knew that 30 minutes is never going to be enough with such much, this level of expertise. Thanks, Zach. Thanks, Stephen. Thanks, Janakiram. I think audience probably will have to go to the next session. It was great having you as part of the panel.
Great.
Thank you very much. Have a great day.
Thanks, Arun. Thanks, guys. Talk to you later.
Bye.
Bye.
Thanks, Arun. Yep, bye.
Thank you.